As a start, I am Omar Sobhy. I am part of the AQC core team, and I am a mentor and the organizer within the Egyptian quantum community in Egypt. And I am a co-founder of quantum educational channel on the YouTube called Quantum Computing in Arabic. I am doing theoretical physics majorly, and I'll be with you in this session today to introduce to you what quantum computing is. But it's always nice to see some picture of our session tonight, and we will start from the very beginning, and I'll try to keep this session as simple as possible in order for everyone that could understand what is actually quantum computing and what is happening within the theory of the quantum. So I have a technique. Whenever I try to study something new, I always tended to make it as simple as possible. So, for example, there are 7 steps of learning. The very first one is understand the topic. So this is what we're going to do tonight. We try to understand what quantum computing is. And in order to do that, we have to ask ourselves like 5 simple questions. The first one is what? Like, what is quantum computing? Second one is why? What is the motive for quantum computing happening nowadays? And the third one is how to actually dive deep in quantum computing and how quantum computer works. And there are fourth and fifth questions, which is when and where, but we'll mainly focus on the first 3 questions, which is what and why and how. So if you ask ourselves what is quantum computing, we would see that quantum computing is mainly divided into 3 major fields. Actually, from its name, quantum computing, we can see that there is a quantum. Quantum is a subfield of the major science of physics, and there is a computing. Computing is, as we know, the computation processes. So let's start with what is physics. Physics is actually try to answer a very, very, very simple question: how everything in the universe works. So how the cars moving, how the earth, how the earth rotating around the sun, and how the whole solar system rotating around around the center of the galaxy. So physics is mainly about try to figuring out how everything in the universe works. This is if we want to just like make one simple sentence that describe the physics. So what is quantum? Quantum is a subfield of physics that is interested in studying the tiniest parts of the nature, which is atoms or particles, or electrons, positrons, and etc. So in order to, if you want to study the motion of how these tiny particles move, this is how we study quantum mechanics. So as a third term in our like big term, quantum computing is computing itself. Actually, humans are very, very lazy. They try to do things in order to make themselves rest and so on. But actually, we can like put it in another way. Like, humans are not lazy. Humans are actually genius, because they tend to give the repetitive tasks or the complex tasks to something that could do better at it and faster. So humans actually are genius. So they give the simple tasks to any machine, and they like make their mind clear if they want to tackle any other complex problems. So this is actually the computing process is using the machine to solve problems and process the information, something to deal with repetitive tasks and so on. So here is the why question. We have done with what question, and here is now the why question. Why quantum computing? So basically, why quantum computing? Actually, the motive of building quantum computers started early in 1974 with the invention of the transistor. So the transistor basically contains some charges, and what you're doing when you want to measure a state of a bit you have is that you take the average of the charges you have in the transistor. And there are Moore's law is telling us that in each year the number of the transistors on a microchip, it doubles about every 2 years with a minimal cost increase since the transistor very first invented. So as we can see here, the things that the science reaches now is Pentium 4 processor, which contains around 1 power 9 transistors. And as we can see that in each year, the number of transistors will begin to be less until we have reached the quantum level. So what is the wrong with that? The wrong is when you take the average, that at some point you won't be able to even measure your state. There would happen to be some information loss. So this is why we needed quantum computing. Actually, Richard Feynman was the first scientist who brought in bring the table this idea of quantum computing. He was doing some quantum simulation experiment, and he said that if we have a quantum computing that could deal with the term of quantum computing wasn't known as this time, but he just said if we have a machine that could work with quantum laws, that's when we can simulate the nature as itself. And this idea has come across to be well presented with Shor's algorithm. Actually, Peter Shor, he invented a very important algorithm in quantum computing. This algorithm solves a problem called the integer factorization problem. So basically, the integer factorization problem is that if you have any integer, the integer consists of 2 prime numbers. Let's say any number. Let's say, for example, 15. The 15 is the multiple of 3 multiply 5. So they call the basis of our integer number. And actually, this important is very important because every website we go on today begins with HTTPS. Actually, S here means secured. It depends on type of encryption called RSA, which is built on the integer factorization problem. To see how much is hard to break in this formula, here is the RSA 192, contains of 192 digits. And actually, these are the 2 prime numbers that if you multiply them, you could get the RSA 192. Sorry, 29. And as you can see, the RSA 129 is successfully factorized on approximately 1,600 workstation worldwide, and it needs around 8 months to solve this problem. And as you can see, here are the already existed, or the existed challenge of RSA. So good luck with solving this to find the two prime numbers of it. And if you have the luck to solve that one, you can win up to $2,000. All right. So I'll go through these slides in fast somehow, because this is not the purpose I want our session to be tonight. I'm just giving you a very simple introduction about what quantum computing is. And actually, quantum computing is part of a very wide range field called the quantum technologies. Sorry, there's some question. Sorry, I think someone got unmuted. Okay. So I was saying that quantum computing is a part of a wide range fields that are called quantum technologies, which include quantum communication and quantum sensing and quantum simulation. Quantum communication is interested in the encryption of our networks and the encryption of our channels and so on. And the quantum sensing is interested in measuring things with extreme precision. And the quantum simulation is interested in simulating the nature. For example, simulating the chemistry equations. And as you can see, there are already a wide range of companies and institutions that interested in the quantum field and already doing research. And actually, in Africa, you can see in Africa, you can see that there... Sorry, come again. Right. So if you have some question, feel free to interrupt me and ask a question. If not, I just ask you to mute yourself so everyone can just focus on the content.
Omar will give them a Q&A time at the end of the presentation.
Sorry.
At the end of the presentation, they can ask the questions after.
Okay, sure. Yeah.
All right, go ahead.
All right. So I was saying that already there are a lot of institutions in Africa that are doing quantum research. And in fact, if you again the mic.
Sorry, can you please all mute your microphones? Lekaya Mark, can you mute your mic? Thank you. Okay, Omar, I think you can go ahead. Omar? Oh, okay, looks like we lost Omar, so we'll reach out to him and give him some time to reconnect.
Right, I'm very sorry for that. My network just cut off. I will share my screen. Right, can you see my screen now?
Yep, everything's good.
Right. Sorry again for this inconvenience. Okay, I was just saying that if you type quantum before each term, quantum machine learning, quantum AI, quantum neural networks, you will find definitely a research area in this spot. Okay. So now here's the core of our session today. Congratulations, everyone. We just reached to the beginning of our session. And this part of our session, we gonna be answering the question, which is how. We will basically try to see the theory behind the quantum computing. So most of the quantum computing programs or courses start with this thing you're seeing now. And I'll just, wait a second, I'll open sheet so we can take, like write some things. Right. So I was saying that most of nowadays, sorry, most of nowadays programs start with this thing. Or it's not like that. And actually, this is a very bad place to start quantum computing, because quantum computing is an interdisciplinary field and is very complex. And in order to start or give some good introduction to quantum computing, we have to start from the very beginning, like how actually quantum computing computers are built. So let's start from the very beginning. From classical computers, actually. We need to start from classical computers. Here's a bit. I hope you all know what the bit is. So the bit is a basic unit in classical computers. So this is a bit. The bit can take two possible states, which is zero, either zero or one. Now, let's say we have 2 bits or 3 bits. How many possible states that these 3 bits could take? So we will start with 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, and until we reach 1, 1, 1. So if you count this, all these states, you will find it's about around 2 to the power n, which is n is the number of the bits you have, which is here 3. So you will find it's 2 power 3, which is 8. So your state could be in only one possible combination of these 8 combinations. So it could be 0, 0, 0, 0, 0, 1, only one state in them. All right, so now we gave just a quick preview or brief about the classical computation. So we said that the transistors reached to a very, very, very small level, which is actually now in the nanoscale. So we want to like go deeper or make it less in size. To do that, scientists like asked, what if we make our transistor the atom itself? So here's an atom. Let's say it only have 2 energy levels, and obviously this is the low energy level, and this is the high energy level. Okay, so these energy levels are, or this atom is non-stable, is not a stable atom in order to like tend to gain or lose electrons. So what we need to do, that we have an electron here. Okay, we want to give this electron some energy in order to transfer from the low energy state or energy level to the higher energy level. I'm very, very sorry. Again, I don't know why the network is keeping cutting off, and we'll proceed just right now. All right. So continue our speaking. I was saying that we have an atom. This atom consists of two energy levels, which is unstable energy levels. And we have an electron here. We want to give this electron an energy to transfer from the low energy level to the higher energy level. So our electron reached here on this energy level, and the, uh, the amount of this energy is the difference between the second energy level and the first energy level. Okay. So why actually we're doing that? We're doing that because we want to represent our qubit in some things that we already know from the classical computers and so on. So we want our 0 and our 1 state in the quantum computing also. So scientists say that, okay, so our energy level will be the state 0, and our higher energy level will be the state 1. So when we give energy to our qubit, we simply transferring from the 0 energy level to the higher energy level, which is 1. And why is this notation? I'll tell you just in short time. Okay, so this system, let's just draw it again here. Okay. This system is a closed system. What does it mean by a closed system? It means that our atom is inside the system in order to not to just to interact with the environment. So the noise affecting it from any other radiations or so on that coming from light, from the universe, and etc. So just we keep it in a closed system or isolated system to not interacting with the environment. And as we just said, here's our 0 and our 1 levels. Okay. So what if we didn't give this electron right here? What if we only give it half the amount of the energy it required to transfer for the higher energy level, which is 1? So here's our system again, or we can just make a copy of that. Oh, all right. Here's our system, and here's our electron, and we'll give our electron only the half amount of energy to transfer to the higher energy level, which is 1. Actually, this energy is insufficient to make it reaches to the higher energy level, but it also can't make it like he has some energy now, so he can't stand in his position. So actually, what is happening is that this electron starts oscillating between the ground state energy level and the higher energy level. So it will be something like that. It's oscillating between the two states. So he stays at the higher energy level sometimes and the lower energy level sometimes, and it keeps this way until this energy is vanished, or if we just decided to take out this energy by doing cooling or something. So if we decided to take this energy back, the electron will return back to its original state. Okay, another question. What if we didn't give it half of the energy? What if we give it the quarter of the energy required? And here is our system again. We can delete that. Sorry. Okay, there's some inconvenience happens. All right, here is our system. And we give it only around quarter of the energy needed. Oh, we will start seeing another different behavior. Would actually see that this electron like tends to go more to the ground energy level, and it stays like less in the higher energy level. And actually, we can write this system of ours, or this state of ours, like represent it. We want to represent it mathematically. Our state, let's name it anything. Let's name it psi. Actually, name the psi. I'm not sure why it's happening. Okay. Okay. All right. We will call our state psi. So psi here represents our state. Okay. So, and our we're going to also represent our zero state, or the ground state of ours, and the higher energy level of ours, which was 1. And we want to write that our system, like our electron right here, it oscillates more to the 0, which is actually an amount that we give it to him, which is a quarter, and it oscillates less to the 1, which will be which will be only sorry, I say something wrong. It will oscillate to the zeros 3/4 times, and to the 1 only the quarter, because this is the amount of energy we give it to him. So here is what we wrote in the very first beginning. So we have our state, and we have our amplitudes, and our 0 state, or the ground state, and again our amplitude, and the higher energy level state of ours. Actually, if you can remember, this is what we wrote here. Congratulations, we reached to understand what is the state meaning, or what the state means. Actually, A and B called the amplitudes. And they are complex number. But here we have a probability. Like what does it mean by probability? If we opened our system right now, if we make a small gap here, so we can measure or know what is our state right now in this minute or in this second. We will take a look, and actually, as we give it only the quarter amount of energy that it's required to transfer to the higher energy level, we know that our state only has a probability 25% to be in the higher level, and 25% to be in the ground level, which is 0. Okay, so this is what our mathematical representation tells us. And the A and B are called the amplitudes, which is or where is A squared plus B squared equal 1. So here we reach to understand what the state is. All right, so we want to understand what is this notation. Like what is this weird sign of greater than and this thing. This notation called Dirac notation. It was invented by a scientist called Paul Dirac. Just a shortcut to help us doing complex or complex computations in the quantum systems. So basically, we'll shortly introduce that in quantum computing or in quantum mechanics in general, we work with linear algebra. Actually, we're working with vector and matrices, which is part of linear algebra. And the vector and matrices, when we come to complex system of quantum mechanics, they're just hard to work with. So Dirac notation make a very simple notations, or Paul Dirac make a very simple notations that could help us simplify the work in the quantum computing or the quantum mechanics in general. So if we just studied our 0 state and our 1 state, we find that actually this notation is a shortcut of this matrix. And this notation is a shortcut of this matrix. This is a very well-known, very popular form used for the zeros and ones. There are another forms, but this is a very most popular one. Just 1 second. Okay. So we can rewrite our state with this form. A 1 0 plus 0 1 which is this is how to present our matrix in the dual form of the normal vector, or even we can make it more simpler than that. Our state here equal to A and B. So it just to know that in quantum mechanics or quantum computing, we work with this notation. Okay, but we can also do the same mathematical work with also the vector representation. All right. So what basically we need to do? Like, in what is the whole idea of quantum computing? Or you have the Pang hackathon. What do we need to do? We have some classical data, or let's say quantum data, or let's go back a little bit and like describe the whole or the general idea. We have some inputs. We want to perform, or like that. We want to perform some processes in these. Let's say call it Y, to reach an output. A very simple idea. So this is what all the quantum work is. So we have, let's say, a quantum data. The quantum data is represented in a form of qubits. And these qubits, as we saw here, is basically vectors. So these qubits is vectors. And we need to perform some operations in this quantum data we have, or these qubits, which is the same. The qubits represented in vectors. So let's take that. Let's say we have some state. Let's call it psi. And we want to perform some operation here to reach an output. Let's call this output psi dash. And let's call our operation here U. Actually, this operation is also matrix. And this matrix, let's say U be a unitary matrix. So what is mean by unitary matrix? Right. We know from classical computations that if we have any, or not from the classical computation, we know in general, if we have any matrix, we multiply this matrix for its inverse. It gives us or it equals the inverse of this multiplication, which is equal the identity. We know that from the classical computation. What is mean by the unitary matrix is that the matrix should do this thing. So let me like put it in another form just to be a clear idea for you. Right. First, let me introduce you to a very popular like term, and we will understand from this term Right, I'm very sorry about this again. My network went off. I don't know why. But let So we said that our matrix is, my internet connection is unstable again. I don't know why. Okay. So we were saying that our matrix is, or our state is represented in matrix. And in order to make some computation, we need our form of this to be something called quantum, or sorry, the complex conjugate transpose. So what does this mean? So here's our state again. Our state equals A, B, and we have another or the same state. The complex conjugate transpose of this state simply will do that. And this would be like that. Our state would be look like that. Actually, this part called kit, and this part called bra. And just to remind you, those were our amplitudes, and also those. But as I said, that these amplitudes are in complex numbers. So this is just the transpose of this complex number we have. So if we want to do an inner product between these two states, it would look like this. Here is our bra part, and here is our kit part. And as a shortcut, we tend to write it this way. Okay. So if we want to do the same thing with our energy levels, or let's say that this is our state, we want to get the gate out of it, which is this. So this state is in this form, and what we do is just that we make it like this. Okay, and same as for the one. Right? So why are we doing this? In order to keep the reversibility. What does this mean by the reversibility? Let's go back to our main idea. Let's say we have state 0. We want to apply some matrix in here. And apply the same matrix again here. In order to reach our state. This state of ours would be also 0. So it's like that we done nothing. We want to do something and redo this something in order to get the same or the original state that we started with. So this state or this matrix that we have. Let's make it. So we have a 0. We want to apply on the 0 some matrix. Let's call this matrix X, and reapply it again in order to get the 0 output. Okay. So let's start first by applying this part. All right. So this matrix, it's actually should be in something like that. 0, 1, 1, 0. And we want to apply this matrix to our state, which is 1, 0. It's just a very, very simple matrix multiplication with just grab the rows, multiply it by the first column, and the second row with the also the first column, which will give us a 2 by 1 matrix. If we multiply the 0 by the 1, it will give us 0, and if we multiply the 1 by 0, the second column, sorry, the first row with the first column, we would get something like that, which is 0 by 1 and 1 by 0, and here are 1 by 1, and here are 0 by 0. Okay, and actually you obviously can see that all of these are zeros, and you could get 0 and 1. So what is this state? If you can remember, this state was 1. We wrote it somewhere here. Yeah, here's our state. If you can remember, this is our state now. So basically what the gate, and here our new term, X is called quantum gate. Or actually single quantum gate, as it operates in only single qubit. So what X what X does, it's actually like make our state the same or the other, yeah, it changes our state from 0 to 1. It flips our state. So this is actually what the X gate does. If we do the X gate again here, as you can see here, if we do it again, it would give us also the 0 state that we started with. So we could just make it here. We want to apply X again on the 1. So here's again 1, 0, 0, or sorry, 1, 0. We want to operate it on our state, which is 1. Yeah, you can do the multiplication, and you would see that we have reached also to the 0 state. So basically our matrix here called X gate. And if we only did it once, as we saw, we'd only get the 1 state. There are multiple gates that do the same thing, and we can find them here. You can find that here's our Pauli X gate, and here's our Pauli Y gates and Pauli Z gates. Basically, these gates do some rotation around something called the blocosphere. I want just emphasize one very important gate here, which is the Hadamard gate and the CNOT gate. So why are specifically these gates are important? Because Hadamard gate do something called superposition. So what is superposition? Superposition is basically if you have a coin and you flip it, if you flip the coin over, this is state that you have when you're flipping the coin. Actually, this is state it represents the superposition. You don't know exactly what is your state in this just frame of time. You don't know. Okay, so if you just want to check whether your coin is head or tail, you have to let it land on your hand, and you just check the state of yours is either heads or tails. So whenever the coin is flipping, you cannot know what is its state right now. So this is basically what superposition is. Is the Hadamard gate. It makes our state in this superposition. Like if you could remember, we talked about that our state oscillates between the two energy levels, which is the zero and the first energy level, or the higher energy level. So basically, these oscillating processes is what superposition is. So right here that this is superposition. So you cannot know for sure your state at the moment unless you break through this closed state, this closed system, and you just take a look or do something we call in the quantum mechanics measurement. In our circuit, here's our circuit. In our circuit, actually, we don't just like get to know this state like that. We do something called measurement. It's like opening the door on our closed system. So the measurement in the quantum looks like that, something like that. And this is how it tells us that our state is now 0. So the measurement simply processes to check what is your state right in the moment. So all of this right here is that this is your circuit or this is your program you're doing. This is the calculations you're doing. You can put any like or you could try different gates in here as we saw them. You could try all of these gates through something called IBM Composer. So basically, here is our interface, and here you can find our qubits. We have now 2 qubits and 1 classical register. Classical register is where we just check our state classically. So you can see that we have. Let's start very first with only 1 qubit. So now we have 1 qubit, and as you can see, our qubit is in the state 0. Okay, as you can see right down here. And from this sphere, you see this is called log sphere. Our qubit is in the state 0. And if we applied the X gate right here, you would see that right. We did the math here. So if we applied, there's some internal connection. Right, I'm hoping that you can hear me and see my screen. Okay, so we did the math of it, and we came out that if you applied the zero, or if you applied the x matrix on your zero state, you would get Z1 state. And yeah, here is that you can find that if you apply the X gate on the qubit of yours, you would find that your state now changes to Z1 state, which is something called the phase change. As you can see in the first, if we remove this, you can see the first that our qubit was in here, and if we applied the X gate, it would change from the 0 to 1, which is down here as if you did 180 degrees reflection on the y-axis. And let's add or try to add some other qubit, and we want our state to be, or it's not necessary right now. We can keep it 1 qubit, and we apply Hadamard gate. So we say that Hadamard gate give us the state of superposition, that we don't know for sure whether our state would be 1 or 0. So as you can see that our state now is 50% in with a probability of 50% to be in the 0, or and probability of 50% to be in the 0 state. And you can see that our qubits have split it into two because we don't know for sure which one would it be. So this is why Hadamard gate is important, because it actually it's originally gave us the powerfulness of the quantum computation. So I want to introduce you to some other concept first before adding some other qubits, which is called the entanglement. The entanglement is also what gives our quantum computers the powerful computation it does. So entanglement basically, let's say now we have got two coins. These two coins is somehow connected with, let's say, some wire or something. But you have the first coin here is its face is the head, and the second coin here, its face is the tail. So they are connected in somehow, which is the upper face is the heads here, and here's the upper face is the tail. So whenever you flipped these states and you let them land down, if you just spotted the second coin you have, you would find that, or you will immediately know that the other coin is the other face. So I'm not sure if you understand that. Let's say you have two coins. These coins here as heads, and okay, this one is the tail. So they are connected in some wire or something, and you want to flip them over. So you throw them out in the air and you let them land down. So you start it. Now your coins have landed on the ground, and you want to know what is the state of this one. Okay, but so you try to spot this one. You found it heads. So you immediately know that the other one is in the other direction. which is, sorry, which is details. Because this is the way you set it set it them in the first place. You set it them to be the upper face here is the head, and the upper face is the tail. So if you just try to make it again, and you found okay, no problem, and you found the first one is tails, you immediately will know that the other one is the heads, because you organize them in this way. So basically, this is the entanglement. If you have any qubits or any uh, entangled states, let's say this is spinning upwards, and they are somehow entangled, you would know, let's say this way. Okay, so this is your states, and you entangle. You know that this system you have, is entangled. Okay, so if you took one qubit of them to a very far place, and the other one to a very far place as well, and you wanted to check what is the state of the first one, because you don't know it, so you decided to like you have your box here. Let's let's make another box here, and you want to know what is the state of the first qubit you have. So you decided to open this box and take a look. You would, for example, let's say it is being downwards. You will immediately know that the other qubit you have is spinning upwards. And whenever you did any phase change, or you did any added some energy, and to make this one spinning upwards, you would immediately find that this one has just in the same second, and the same femtosecond is now spinning downwards. This is what entanglement is, in very simple, which is actually very insane, because we know that from the special, or the general relativity of that as put by Einstein, that the light of speed is the most like maximum speed that anything could go with. But here you can find that this thing happened instantaneously in uh, the same second, or the same femtosecond. It doesn't take any amount of time, which is actually break the theory of relativity. And actually, Einstein called this process, or this phenomena, as spooky. Not sure, I'm not remembering the term, but as spooky action at a distance, as far as I remember, because this very interesting. Yeah. So if we want to do these entangled states in our composer, as you know, we now definitely gonna have or gonna need another qubit, because as you can see here, that we have two states. There must be two states in order to be able to make the entanglement. You cannot make entanglement with only one state, which is obvious. So how entanglement actually is done? We take the Hadamard gate, which is put our state in the superposition, and we apply something called CNOT gate. Okay, the time won't. The time is now okay. So I have less than 1 hour. Okay. All right. So I'd have gone and explained to you these processes mathematically, but we have no time for doing that. So I'll just make some headlines, and you can go deep and deep or more dive deep in this area. So just to make as a headline, in order to do an entanglement, we need to put the Hadamard gate, and after it the CNOT gate. Basically, what CNOT gate does is that if we let's remove this for now. If we have our state, like this state is started or originally is 0. Okay. Uh, let's try to write it down for better. Okay. So we started with 0 state, and we have our circuit here. We want to apply the CNOT gate. So what does the what the CNOT gate do is that if we started here with the 0 state, and let's say we have some other qubit here, let's call it psi, and we want to know what is the state of this one and the state of this one. So if we apply CNOT gate, and we know that this state of ours is 0, as we write it down. Let's like do some tracking of our state. We find that our state moving here, right? And it will display it. Or actually we should okay. So our state will go here for simplicity and be 0 as it is. And actually our state here will be also 0. So let's try something else. Let's try to change this state and make it 1. Okay. If we try to track our state again, we will find that this state of ours also passed right here and continued to be 1. But here's the thing, our state down here, it will change. If we say that, for example, this state R is 0 also, this state of ours, 0, would change from 0 to B1. So this is what the CNOT gate does, and we could see here, it here better. So if here's our state, our state is now in 0, and this is also 0 state. If we applied the CNOT gate, there is nothing happening. The first one is 0, and second one is 0, as we can see from the table here. The first one is 100% 0, and also the second one is 100% 0. But if we try to apply the X gate before, actually this mutation or this thing is the X gate. Okay, it's represented this way in the interface. If we try to put our state here, that we will find that our state is now 1. So basically, what we did right now is that we changed this state of ours from 0 to 1. Okay, and then we applied the CNOT gate. So now our first state is 1, and also our second state is 1. Notice that, let's go here. Notice that we started with the first state with 1, but the second state was 0. Okay, and then we applied CNOT gate. So it finds that this state of ours is still 1, but this state of ours has changed to be has changed to be 1. So this is what CNOT basically does. And if we want to make our entanglement, we use this setup, which we put the Hadamard gate, and then we put the CNOT gate on our first qubit, targeting the second qubit. So these two very important phenomena is what gives the quantum computing its powerful computation capabilities. And actually, this was some very heavy introduction. It feels normal if you didn't understand any like most of the things. I was like this in the beginning, but just get yourself familiar every section or every course you take. Get yourself familiar with these things, and also start try to do or to search more in the mathematics of these aspects. As I said, as the time actually won't help us to dive deep in the mathematics more than that. But just like I hope I give you some introduction on what quantum computing is. And actually, if we like say one more little thing, this is what you will be doing in your hackathon, or even if you did any other project by yourselves, that you will have some input, and you want, or let's make it simpler than that, you have some input. You will apply some matrix on that. It could be 1 more, 2, 3, and etc. And you will find or you will get an output. This is what you will be doing in your hackathon, or in any other project you'll be doing. So don't forget that. So for example, one project I worked on was in weather forecasting in Egypt. So basically, what we were doing that we were doing a quantum or a hybrid quantum machine learning model that could expect the air quality within the upcoming 3 days. So we have some data or classical data. These data we have, they are classical data. And we want this classical data to be an input to our hybrid quantum classical quantum machine learning model. So there are something called feature map. Feature map is responsible for doing this thing. Is that it takes your classical data to doing some matrix multiplication of it to make it quantum data, which will be in the form it will be in a form that you or your model would understand, in order to like do the program or the computation you will be doing on it, in order to get output from the quantum computing program you have. So this is the pipeline of your work that should be like if you just decide to work in quantum machine learning or uh, any other track or field you decided to do. This is what basically the pipeline. You have some practical data, you want to do some changes in it in order to be in quantum form, and you take this quantum data you have to do some operations or whatever circuits you need to apply on it. And I didn't mention that, but this actually code circuit, it actually lacks the measurement here. It lacks the measurement. And here also. But this is called circuit, and the other one here called circuit, and also what we have done before called circuit. So this is your quantum circuit, basically, yeah. All right. So I didn't want this session to be only some lecture or some sort of lecture. I wanted to be like a real workshop. So you can scan this Google Colab, and it would, sorry, land you here. And you could find some examples or you can do what we have done like in programming. So we're using a framework called Qiskit. There are some other frameworks that you could work with, but Qiskit is the most popular one. Here you can find that our circuit. So here we establish our circuit, and it contains 2 qubits and 2 registers. And here we apply the CNOT gate on our circuit. Here we applied it into the qubit 0 and targeting the qubit 1. And here we applied quantum Hadamard gate. And here we are doing the measurement. And this is just a library that draw our circuits. So you could find here our circuit, and actually this is a reversed circuit. And here is your part. You should answer what if we change the order of the gate? Do you think the entanglement would still happen or not if we change the order of the Hadamard and the CNOT? As you can see here, that this is our order, but here in the program we changed it. So you should answer the question: what if we change the order of the gates? What do you think that the entanglement will still work? Why or why not? You could try it mathematically, or you could just try it in the composer, or just with intuition. You can answer this question. And as a second challenge, also you can answer, or you can write this quantum circuit if you'd like. You're not obliged for that, but it would be nice just to familiarize yourself with the answer. I see some comments here. Yeah, sure. Yeah. Okay. So here's again the QR code. Feel free to scan this. And we finished our session for today. And it would be nice to connect with you. Sorry. Yeah, it would be nice to connect with you through my LinkedIn here. And now here's the time for our question. I hope you scan this QR code and the other QR code. And we still have, yeah, maybe 15 minutes for the question. So if you have any questions, just type in the chat or open mics or so on.